Okay, so the objective for the redesign, usually in the engineering design, the objective is not really different from the objective of you buying a new car or something, right? So basically you want to minimize a combination of the initial investment and the cost of operation. So in this case, the initial investment is how many airplanes you have to get ready for towing the passenger airplanes, which would presumably fly between East Coast and West Coast. All right, and the cost of operation involves how much does it take to maintain, charge the airplanes, and fix anything that needs replacement and things like that. And the balance between the initial investment and the cost of operation depends on a lot of like financial situations, the interest rate, how enthusiastic your investors are, etc. So all of these are important, but like pretty far away from aerodynamics. Therefore, we just assume different components have the same cost, and the different components also have the same cost of operation per weight. Okay, under these assumptions, all of these objectives of minimizing initial investment and cost of operation boils down to minimizing the total mass of the airplanes you're having to get ready on the ground for the passenger flights. So our surrogate objective for next week is just minimizing the total mass of the towing airplanes along this 3,000-mile route. All right. I mean, in reality, you probably have the cost per weight of different components and the cost of operation per weight of different components. But let's just assume they are all equal for the purpose of aerodynamics. Now, since we are looking at mass, you cannot really think about minimizing mass without really any structural considerations. But again, for the purpose of focusing on aerodynamics, let's just make some very simplistic assumptions. I mean, as simple as possible assumptions about structures. If you're more interested in structures, you can probably point out the deficiency of all of these assumptions and build better models. But let's just ignore these for the project. So for example, we assume an empty fuselage weighs the same as the batteries it can carry, right? So if a fuselage carries, let's say, 5 tons of battery, right? We assume the structure has to weigh 5 tons. So that's as simple as you can get. All right. And the wing, we assume it can carry as much battery as you can fit into 50% of the volume. So what does that mean? That means that the wings, because so basically the weight of the empty wing does not go up if you put more batteries onto it, because it's a pretty reasonable assumption, I mean, although it looks counterintuitive, because the weight of the battery is distributed along the whole span of the wing, right? So you don't really need to add that much more structure if you put more batteries that are distributed along the wing. In some cases, it actually helps you to reduce the bending moment on the root of the wing. So let's just assume you can fit 50% of the wing volume as batteries. And this is going to be important next week when you actually start to optimize the shape of the wing. You may decide to make it thicker, right? So you can fit in more batteries, but you'll be suffering aerodynamic consequences potentially, right? You may decide to change the sweep, and you may decide to change the airfoil shape, etc. Right? Okay, so basically, how much batteries you can carry into the wing only depends on its geometry, and it has no weight consequences. And the empennage, I mean, for stability purposes, let's just say it weighs 3% of the rest of the airplane. So just add up all the weight of the fuselage, wing, engine, and add up 3% for the empennage. So again, as simple as you can get. And the engine, let's assume it weighs, we don't really know what technology is going to go into such big like aviation electric motors, etc. yet. So let's just make a pretty random assumption. I mean, not really random, but it's very not very precise assumption. Let's say per megawatts of power, the whole engine, including the power, like the motors, the propellers, whatever that is part of the engine, 200 kilograms per megawatt of power. All right. Finally, for the wing, which so for this week, it doesn't have to be as complicated, but because we are going to be redesigning the wing next week, so we'll just anyway start with a more complicated assumption that will be necessary for you to not get away with ridiculous designs. All right. So the mass of the wing is a non-dimensional constant times the reciprocal of the thickness to chord ratio. So what does that mean? That means if you can make a thicker wing, it helps with the structure, right? So you can get away with a lighter wing if the wing is actually thicker. So that's why, like, if you're a pure structural engineer, you would like a wing to look like a box, right? So thickness to chord ratio is a smaller thickness to chord ratio is going to increase the weight of the wing. And this thickness to chord ratio is the chord considering the sweep. So that's not the aerodynamic chord, right? An aerodynamic chord would follow the direction of the free stream to measure how much chord the wing has. This C orthogonal is the chord from a structural perspective. It is if you cut orthogonal to the spar of the wing. All right, that's basically taking into consideration of the sweep. All right, that matters for structural reasons and therefore matters for the weight.
Could you sketch that super quick? I don't think I understood that.
Oh, sure. Okay. So let's say this is the free stream. Right, that's the wing. All right. So this is the usual chord when we talk about aerodynamics. But the C orthogonal is this. All right. The thickness doesn't matter. The thickness is basically the maximum thickness of the airfoil. But the chord is different depending on are you looking at aerodynamics or are you looking at structure? All right. So here comes the aspect ratio. So for this week, this is just going to be a constant because the aspect ratio of 25 degrees is the Boeing 737's. Sorry, not the aspect ratio. Not the aspect ratio. The aspect ratio. Oh, okay. I didn't include it here, but you can look it up, right? We have the span and we have the wing area. The aspect ratio is equal to the span divided by the mean aerodynamic chord. And the mean aerodynamic chord is defined as the area, the platform area of the wing divided by the span. So you can compute the aspect ratio that way from the geometry you looked at last week. All right. And